Our universe is a masterpiece with most of its canvas hidden from view. We see the stars and galaxies, the grand spectacle of the cosmos, but this is only the surface layer. Beneath it, physicists and philosophers propose a deeper reality, a shadow cosmos of hidden dimensions, parallel worlds, and forces that rewrite the rules of existence itself. By the end of this exploration, you will journey through 30 of the most profound theories ever conceived about these secret layers of reality. We will confront ideas that suggest everything you know is a projection, a simulation, or just one page in an infinite cosmic library. What if dark energy is a leak from another dimension? Could your consciousness be a quantum process intertwined with the fabric of spacetime itself? This is not just science, it is a detective story on the grandest scale, where the clues are written in the afterglow of creation and the silent pull of invisible matter. Each theory is a key, attempting to unlock a door to a reality far stranger than fiction. Are you ready to question the nature of everything you think is real? The first key on our ring opens the door to a staggering possibility. It is the multiverse hypothesis, the idea that our universe is not alone, it is not even special. It is simply one bubble in an endless cosmic foam, one page in a book with infinite chapters. This single theory has many faces, each emerging from a different branch of physics, yet all pointing toward a reality of unimaginable plurality. From cosmology, we have the inflationary bubble multiverse. Picture the Big Bang not as a singular event, but as a never-ending process. A boundless, hyper-fast expanding energy field called the inflaton field stretches forever. Within it, random quantum fluctuations can cause pockets of this field to collapse, each collapse sparking a new Big Bang and birthing a new, self-contained universe with its own unique laws of physics. Our entire cosmos is just one such bubble, floating in an infinite sea of other bubbles forever out of reach. This explains a profound mystery, the fine-tuning of our universe. Why are the fundamental constants, like the strength of gravity or the mass of an electron, so perfectly set to allow for stars, planets, and life? In an infinite multiverse, every possible combination of constants exists somewhere. We simply find ourselves in the one bubble where the numbers are right for us to be here to ask the question. Then, from the bizarre world of the very small, comes the many worlds interpretation of quantum mechanics. In a standard quantum experiment, a particle exists in a blur of all possible states until it is observed, at which point it seemingly picks one. Many worlds proposes a radical alternative that it never chooses. Instead, the universe itself splits. At every quantum decision point, reality branches. In one branch, the particle spins up, in another, it spins down. Both are equally real. Every possible outcome of every quantum event happens, creating an ever-expanding tree of parallel universes. In one world, you are listening to this script. In another, you decided to watch something else. In countless others, versions of you live every life that quantum probability allows. Finally, string theory offers the brain multiverse. In this view, our three-dimensional universe is a membrane or brain floating within a higher dimensional space. Other brains, other entire universes, could be floating right alongside ours in these hidden dimensions, separated by a gap we cannot cross. Sometimes these brains might even collide with a cataclysmic impact that could look from inside one of them like a Big Bang. This paints a picture of a cosmic archipelago, island universes adrift in a hyperdimensional ocean, occasionally brushing against one another with universe-shattering force. Together, these variations on the multiverse theme challenge our deepest assumptions about reality. They suggest that every accident of history, every chance encounter, and every road not taken is not lost. Somewhere in another layer of existence, it is all happening. The universe is not just vast, it is endlessly prolific, writing every possible story simultaneously. If the multiverse is a cosmic archipelago, then dark matter and dark energy are the invisible ocean holding it all together. These two mysteries constitute 95% of everything in existence, yet we cannot see them, touch them, or explain what they are. They are cosmic ghosts felt only through their immense gravitational influence on the ordinary 5% of stars and galaxies we can observe. But what if these are not substances at all? The second key suggests they are not hidden things, but hidden places. They could be the gravitational echoes of extraspatial dimensions, folded so tightly around our own reality that we are forever blind to them. Consider gravity, the force that sculpts galaxies and bends light. It is astonishingly weak compared to the other fundamental forces. A small refrigerator magnet can defy the gravitational pull of the entire Earth. Why is the universe's master architect so feeble? One compelling answer is that gravity is not weak, it is diluted. It is the only force that can seep out of our three-dimensional universe and into these extra, compact dimensions. Picture our reality as the surface of a vast, taut sheet. This sheet exists within a much thicker space, a higher dimensional bulk. Gravity, unlike light or matter, is not confined to the sheet. Its influence spreads out into the bulk, thinning its effect within our familiar dimensions. From our perspective on the sheet, it appears weak. This leakage could solve the dark matter puzzle. The extra mass we detect holding galaxies together might not be from invisible particles, but from the gravitational pull of ordinary matter residing in a neighboring dimension, just a microscopic distance away in a direction we cannot point to. Our galaxy's rotation is influenced by matter we cannot see because it exists in a parallel layer, tugging on us gravitationally through the fabric of the bulk. This is the core of models like the Randall-Sundrum brane theory. Our universe is a three-dimensional membrane or brane adrift in a warped higher dimensional space. All the particles that make up you, me, and every star are stuck to this brane like dust on a soap bubble. But gravity, represented by hypothetical particles called gravitons, can move freely through the higher dimensional bulk. This warping of the bulk geometry could naturally explain why gravity is so weak and where the missing mass we call dark matter truly resides. As for dark energy, the mysterious force accelerating the expansion of the universe, it could be a constant pressure from the bulk itself, a gentle push from the hidden dimensions that is steadily inflating our cosmic bubble. These ideas transform the universe from a collection of invisible stuff into a multidimensional labyrinth. The darkness we have been chasing for decades may not be a substance, but a shadow, the silhouette of a reality with more directions than we can possibly perceive. This journey into hidden dimensions leads us to a third key, one that questions the very nature of space itself. It is called the holographic principle, and it proposes a truth so counterintuitive it feels like science fiction. Everything you see and experience, the entire three-dimensional volume of our universe, might be nothing more than a projection, a cosmic hologram. Its source code is painted onto a distant, two-dimensional surface at the very edge of everything we know. The idea did not emerge from pure speculation. It was forced upon physicists by a deep paradox at the heart of black holes. A black hole, according to the rules of quantum mechanics, has entropy. This is a measure of its hidden information, its internal disorder. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. It was as if all the information about everything that ever fell into the black hole was not stored inside its vast interior, but was somehow encoded pixel by pixel on its spherical surface. This was the first clue that the information content of a region of space might have a two-dimensional limit. The holographic principle takes this radical notion and applies it to the entire cosmos. It suggests that all the information needed to describe every star, every planet, every thought in your head, every event that has ever happened within our universe can be completely represented on a giant celestial shell that surrounds us. Our rich, three-dimensional reality of depth, texture, and motion is like the holographic image that springs from a flat, laser-etched plate. The plate contains all the data, and the three-dimensional illusion emerges when you shine the right light on it, which in this cosmic analogy is the fundamental laws of physics. In this view, spacetime itself is not fundamental. It is a derived phenomenon, an emergent property of quantum information entangled across that distant boundary. Think of a high-definition television screen. The image appears to have depth and life, with characters moving through three-dimensional spaces. But every detail of that scene is actually stored and processed as a two-dimensional array of pixels on the screen's flat surface. The holographic universe theory says we are inside that illusion. The screen is the boundary of our observable universe, and the pixels are unimaginably tiny Planck-scale units of information. This reshapes our understanding of reality at the most basic level. It implies there is a fundamental limit to how much information any region of space can contain, defined not by its volume but by its surface area. It also offers a potential path to reconciling the two great but incompatible theories of physics, quantum mechanics and general relativity, by describing gravity and spacetime as emergent from quantum information processes on a lower dimensional surface. So, the next time you look up at the night sky, consider a dizzying possibility. The vast, three-dimensional expanse you're gazing into, with its swirling galaxies and infinite depth, might be the grandest illusion of all. You are not looking out into space, you are looking at a projection, a shimmering holographic display whose source code is written on the furthest wall of existence. But if our reality is a holographic projection, who or what is running the projector? This leads us to a fourth key, a theory that has leapt from science fiction into serious philosophical debate. It is the simulation hypothesis, the idea that everything we perceive, from the cosmic expanse to the feeling of sunlight on your skin, is not base reality. It is an artificial construct, a digital simulation of staggering sophistication, running on the hardware of a civilization so advanced we would perceive their technology as magic. The argument gained mainstream traction through philosopher Nick Bostrom, who framed it as a logical trilemma. He proposed that at least one of three statements must be true. First, that almost all civilizations at our level of technological development go extinct before becoming capable of creating realistic simulations. Second, that almost all advanced civilizations lose interest in creating such simulations. Or third, that we are almost certainly living in a computer simulation. The reasoning is statistical. If even a single advanced civilization survives and chooses to run ancestor simulations, detailed recreations of their own past or of possible worlds, they could generate a near infinite number of simulated realities. The number of simulated minds would vastly outnumber the biological minds in the original base reality. Therefore, if such simulations are possible, it is far more likely that we are one of the countless simulated beings than one of the rare original ones. Figures like Elon Musk have pointed to the rapid, exponential advancement of our own technology as a clue. From simple pixelated games to immersive virtual realities in just decades, the trajectory suggests that a civilization thousands or millions of years more advanced could create a simulation indistinguishable from reality for its inhabitants. Where might we look for evidence for glitches in the matrix? Some point to the fundamental weirdness of quantum mechanics. The way particles exist in a haze of probability until observed seems almost like a rendering optimization, a program that only calculates the precise details of a system when someone is looking at it to conserve processing power. Others look to the fabric of spacetime itself. At the incredibly tiny Planck scale, our smooth, continuous universe appears to become grainy and discrete, like a digital image breaking down into individual pixels when you zoom in too far. This finite resolution of reality could be a sign of the underlying computational substrate, the pixel size of the simulation. Even the very laws of physics, which appear as elegant, immutable mathematical equations, could be seen as the beautifully coded rules of the program. This is not a call to nihilism, but a profound recontextualization of existence. If true, it means the quest for knowledge is not about discovering nature's laws, but about reverse engineering the source code of our reality. Every scientific experiment becomes a way to probe the parameters of the simulation, to understand the rules set by the programmers. It places consciousness itself at the center of the mystery, for in a simulated world, our subjective experience is the primary output, the very point of the program. The universe may not just be stranger than we imagine, it may be engineered. Yet another possibility rewrites the very beginning of our story. This fifth key is the theory of the ekpyrotic and cyclic universes, and it replaces the single, fiery birth of the Big Bang with an endless cosmic waltz. In this vision, our universe is not the first and only chapter. It is merely the latest iteration in an infinite series of cosmic cycles, each born not from a mysterious singularity, but from a titanic collision. The stage for this drama is set within the hidden dimensions of string theory. Recall the idea of our universe as a three-dimensional membrane or brain floating in a higher dimensional space. Now imagine another brain, a parallel universe, floating on a parallel course in that same hidden bulk. They are drawn together by a force, perhaps gravity, moving slowly and inevitably toward one another. When they finally meet, they do not pass through each other, they collide, and that collision, from the perspective of beings living on one of those brains, is an event of unimaginable energy and heat, a release that looks, for all intents and purposes, like a Big Bang. This is the ekpyrotic scenario. The Greek word means conflagration, and it is an apt description. Our universe was not born from nothing. It was reborn from the ashes of a previous cosmic phase, ignited by the impact with its neighbor. This elegant idea solves several profound puzzles left by the standard Big Bang model. The first is the horizon problem. Observations show the universe is remarkably uniform in temperature in all directions. But in the classic Big Bang, there was not enough time for light or heat to travel across the vast cosmos to even out these differences. How did distant regions coordinate? In the cyclic model, the previous cosmic cycle lasted for an eternity. Our observable universe was once an infinitesimally small patch on the pre-collision brain, a patch that had more than enough time to become smooth and uniform before the collision stretched it into the vast cosmos we see today. The second puzzle is flatness. Our universe's geometry appears incredibly flat, a perfect balance between expansion and contraction. The Big Bang requires this flatness to be an impossibly precise initial condition, like balancing a pencil on its tip for billions of years. In the cyclic universe, each collision and subsequent expansion naturally drives the geometry toward flatness over countless cycles, like rolling a ball in a bowl until it settles at the bottom. There is no need for a miraculous starting point. The most profound implication, however, is the nature of time itself. There is no true beginning and no final end. There is only the cycle. Each universe expands from the collision, cools, forms galaxies and stars, and eventually becomes cold, dark, and empty over trillions of years. But as it expands, the gravitational pull between the brains draws them together once more, setting the stage for the next collision, the next Big Bang, and the next universe. In this view, the cosmos is eternal, breathing in and out in cycles of unimaginable duration. Our entire history, from the first instant to the last fading star, is just one heartbeat in an infinite cosmic life. Could we ever find evidence for such a breathtaking idea? Proponents suggest a telltale sign might be imprinted in the fabric of spacetime. The specific nature of the brain collision could generate a unique pattern of primordial gravitational waves, ripples in spacetime from the universe's birth. Future observatories designed to listen to these echoes from the dawn of time might one day hear not the shout of a singular beginning, but the resonant note of an eternal return. But eternal cycles of creation pose a profound and deeply unsettling question about consciousness itself. If the universe lasts for an effectively infinite amount of time, what is more likely to spontaneously appear, a complex, ordered cosmos like ours, or a single, self-aware mind floating in the void? This is the Boltzmann brain paradox, a sixth key that turns cosmology into a crisis of self-trust. It begins with a fundamental principle of physics, the second law of thermodynamics, which states that disorder or entropy always increases over time. A cup of hot coffee cools down to room temperature, its heat dissipating into the air. It never spontaneously reheats itself. The universe is on the same path, slowly evolving from a state of low entropy, like the hot, dense, ordered beginning of the Big Bang, toward a cold, dark, high-entropy equilibrium trillions of years from now. However, statistical mechanics tells us that while entropy overwhelmingly tends to increase, random fluctuations can still occur. In a room full of air, all the molecules could, by sheer chance, suddenly rush into one corner, leaving a vacuum everywhere else. It is staggeringly improbable, but given enough time, it is not impossible. Now, apply this to an eternal or infinitely large universe. Given an endless amount of time, every possible fluctuation, no matter how improbable, will eventually happen. This includes a random, momentary assembly of particles that perfectly mimics a fully formed, conscious human brain, complete with a lifetime of detailed, coherent memories and sensory experiences. According to the math, in a truly eternal cosmos, these disembodied, self-aware fluctuations, called Boltzmann brains, would be vastly more common than the gradual, orderly evolution of stars, planets, and biological life. You are far more likely to be a momentary accident of entropy, a brain that popped into existence just a moment ago with the false memory of reading this sentence, than you are to be the product of 13.8 billion years of cosmic evolution. The implications are terrifying for science. It pulls the rug out from under all our observations. How can we trust anything we think we know about the universe's history, from the fossil record to the cosmic microwave background, if all that data could simply be an elaborate, pre-packaged illusion in a mind that just began existing? The entire edifice of cosmology collapses into solipsistic doubt. This paradox is not just a philosophical curiosity. It is a serious problem that modern cosmological models must confront and resolve. If a theory of the universe, like certain models of eternal inflation, predicts that Boltzmann brains should outnumber ordinary observers like us by an infinite factor, then that theory is likely wrong, or at least incomplete. Our very existence as coherent observers embedded in a long, structured history becomes powerful evidence against certain visions of reality. It forces physicists to seek models where the conditions for genuine, sustained complexity are not drowned out by statistical noise. The universe must be a place where minds like ours are not cosmic accidents but expected outcomes. So this eerie thought experiment acts as a filter, a reality check on our grandest theories. It asks us to consider not just how the universe works, but what kind of universe we, as conscious beings within it, are most likely to find ourselves in. The answer must be one where we are real, and our memories are not a lie told by random chance. The unsettling paradox of Boltzmann brains forces us to seek a cosmos where structure is not a fleeting accident but a fundamental feature. One of the most dramatic structures in existence offers a startling answer, a seventh key that turns our perspective inside out. This is the black hole universe theory, the speculative idea that our entire cosmos, from the faintest quasar to the planet beneath your feet, exists within the event horizon of a colossal black hole residing in a much larger parent universe. To grasp this, we must reconsider the nature of a black hole's heart. In Einstein's general relativity, the crushing gravity at a black hole's center creates a singularity, a point of infinite density where the laws of physics as we know them break down completely. But what if that breakdown is not an end but a transformation? Some physicists like Nikodem Poplawski propose that the extreme conditions at the singularity could trigger a bounce, a reversal of collapse into an explosive expansion. In other words, the singularity of a black hole in a parent universe could be the Big Bang of a brand new baby universe within it. Our own Big Bang, then, would not be the absolute beginning of everything, but the rebirth of matter and energy that fell into a black hole in a cosmos that came before. This reshapes our understanding of cosmic boundaries, the event horizon. The point of no return for anything falling into a black hole would not be a destructive wall. From the inside, it would become the ultimate cosmic horizon, the limit of what we can ever observe. Nothing from our parent universe could ever cross in, and nothing from our universe could ever cross back out. We are permanently but peacefully isolated within our own cosmic bubble. This provides a natural explanation for why our universe appears so uniform and flat. All the matter and energy that formed our cosmos entered through the same narrow gateway, the black hole's singularity, and was stretched and smoothed during the violent bounce and subsequent inflation. The implications cascade into a breathtaking fractal vision of reality. If our universe is inside a black hole, then every black hole that forms within our cosmos, from the remnants of dead stars to the supermassive giants at galactic centers, could itself contain an entire new universe within its own singularity. Our universe would be both the offspring of a black hole and the womb for countless others. This creates a cosmic matryoshka doll, an infinite nesting of universes within universes, each with its own potentially different physical laws born from the unique conditions of its parent black hole's formation. This radical perspective even offers a fresh angle on one of physics' greatest puzzles, the black hole information paradox. The paradox asks what happens to the information about matter that falls into a black hole if the black hole eventually evaporates via Hawking radiation. Is that information destroyed, violating quantum law, or is it somehow preserved? In the black hole universe scenario, the information is never lost. It is simply transferred, encoded into the very fabric of the new universe that sprouts from the singularity. The information that made up a star that collapsed long ago in a parent cosmos becomes part of the initial conditions, the DNA, of an entirely new reality. This idea also revives the concept of white holes, the theoretical time reversal of black holes. While a black hole's event horizon is a one-way surface things can enter but never leave, a white hole's horizon would be a one-way surface things can emerge from but never enter. In this framework, our universe's Big Bang could be seen as the explosive output of a white hole, the other end of the tunnel that began as a black hole collapse elsewhere. We are not in the grave but in the cradle. We are living in the aftermath of a cosmic rebirth, looking out at the expanding interior of something that, from another perspective, is the most forbidden region in all of existence. The universe is not just stranger than we imagine, it might be nested inside the greatest mystery of them all. The idea of living inside a cosmic matryoshka doll is dizzying, but what if the nesting happens not just to universes but to the very paths of our own lives? This eighth key returns us to the branching multiverse of the many worlds interpretation, but with a deeply personal and unsettling twist. It is called quantum immortality, and it suggests that from your own subjective point of view, you might be impossible to kill. The logic stems directly from the core premise of many worlds. At every moment where quantum chance plays a role, reality splits. When you flip a coin, the universe divides. In one branch, it lands heads, in another, tails. Both outcomes are equally real. Now, extend this principle to a life or death scenario. Imagine a theoretical experiment, a so-called quantum suicide machine. It is set up so that a single radioactive atom triggers the device. In any given second, there is a 50% chance the atom decays. If it does, the machine fires a lethal bullet. If it does not, it does nothing, and a counter clicks over to record one more second of survival. From a classical perspective, if you press the button, you have a 50% chance of dying in the first second. In the many worlds view, however, the outcome is not random. It is deterministic for the entire multiverse. The universe splits. In one branch, the atom decays and you die. In the other branch, it does not, and you live. The experiment continues to the next second, splitting again. After 1 minute, there are a staggering number of branches. In the vast majority of them, you are dead, but there will always be a subset of branches, however statistically tiny, where the quantum dice kept rolling in your favor, second after second, and you remain alive. The key question is, which branch do you experience? Quantum immortality posits that consciousness can only follow a continuous thread of experience. You cannot subjectively experience being dead. Your awareness is tied to the existence of a living brain. Therefore, at every splitting, your conscious self will always find itself in one of the branches where you survive. From your perspective, the gun simply never fires. The counter would just keep clicking upward second after second, minute after minute, in defiance of all probability. You would witness an impossible run of luck. This thought experiment scales to any probabilistic mortal danger: a car accident, a falling piano, a terminal illness. In the branching multiverse, there will always be some timelines, however unlikely, where you survive, and your consciousness, argues the theory, is perpetually shepherded into those timelines. The implications are profound and deeply strange. It suggests a form of subjective eternity. As long as there is any physically possible quantum pathway for your continued existence, no matter how improbable, you will experience it. You could live through the heat death of the universe, finding yourself alone in a freezing void for eons, sustained by vanishingly rare quantum fluctuations that provide just enough energy to maintain your conscious processes. It transforms death from an endpoint into a road you never take, a branch your awareness never follows. This is not a recipe for invincibility, of course. You would still age, and if all possible quantum paths lead to biological death with no continuation of consciousness, then that final branching is one you cannot avoid. But it forces a brutal philosophical question. Are the people we love who die simply branching away from us, their conscious experience continuing in another reality where they survived the accident or beat the illness? The theory offers a cold, mathematical form of solace that feels more like existential dread. It also highlights the solipsistic nature of the idea. While you might subjectively live forever, everyone else you know will observe you die in almost all branches. Your eternal experience comes at the cost of perpetual separation from the rest of humanity in nearly every version of reality. Quantum immortality is less a theory to be proven and more a logical consequence of taking the many worlds interpretation to its extreme. It shows that when we peel back the layers of reality, we are confronted not just with cosmic mysteries, but with intimate, unsettling questions about the nature of our own existence and what it truly means to be a self, navigating an infinite tree of possible lives. While quantum immortality offers a strange form of personal eternity, the universe itself may be on a collision course with a very different and far more destructive kind of fate. The ninth key on our ring is perhaps the most violent end imaginable, driven by a phantom. Not a ghost, but a hypothetical form of dark energy so potent and bizarre it is called phantom energy. To understand its terror, we must revisit dark energy, the mysterious force causing the universe's expansion to accelerate. In our current best model, dark energy behaves like a constant, a steady pressure inherent to the fabric of space itself. It is represented by a number called the cosmological constant. But what if dark energy is not constant? What if it grows stronger over time? This is the essence of phantom energy. Its density would not dilute as the universe expands. Instead, it would actually increase, making the repulsive force of dark energy more and more powerful with every passing moment. The consequences of such a scenario are not just dramatic, they are apocalyptic. It leads directly to a theory of the universe's end known as the Big Rip. Imagine the acceleration of cosmic expansion starting as a gentle push, but becoming a relentless, ever-strengthening shove. First, the force would overcome the gravitational glue holding clusters of galaxies together. These vast islands of stars, bound for billions of years, would be flung apart into the deepening void. Next, the phantom energy's grip would tighten on individual galaxies. The Milky Way would be torn asunder, its spiral arms shredded, its stars scattered like dust in a hurricane. Then it would reach for solar systems. The sun's gravity would be rendered meaningless. Planets would be ripped from their orbits, cast adrift into the endless, accelerating dark. But the phantom does not stop at astronomical scales. As the expansion grows exponentially violent, it would eventually overcome the forces that hold matter itself together. It would target our very planet. Earth would be pulled apart, mountains crumbling into space. Then it would come for you. The electromagnetic forces that bind your molecules would be defeated. Your body and everything around you would disintegrate into a cloud of subatomic particles. In the final instant, even the nuclei of atoms would be shredded, protons and neutrons torn apart into quarks and gluons. The universe would end not with a whimper, not with a freeze, but with a scream of spacetime itself, rending every structure, no matter how small, into its most fundamental, non-interacting pieces. The timeline for this horror is shockingly calculable. Based on certain phantom energy models, if this is our universe's true destiny, the end could come in as little as 22 billion years from now. While that seems an unfathomably long time, consider that the universe is already 13.8 billion years old. On a cosmic calendar, the Big Rip could be closer to us than the Earth's formation is to today. Is there any evidence for such a terrifying possibility? The search is ongoing and hinges on precisely measuring the equation of state of dark energy, a parameter denoted by the letter W. If W is exactly -1, dark energy is constant, leading to a slower, colder end. But if observations ever conclusively show that W is less than -1, that dark energy's strength is increasing, it would be a strong hint that phantom energy is real and the Big Rip is our ultimate destiny. Current data from telescopes mapping the large-scale structure of the universe and the cosmic microwave background are incredibly precise, but they still allow for a slight possibility that W could dip below that critical threshold. Every new observation is a test not just of how the universe behaves, but of how it will end. So the phantom is not yet seen, but it haunts the equations of cosmology. Its potential existence forces us to confront a universe that is not just expanding, but that possesses a latent self-destructive fury, a hidden layer of reality that could one day unmake every single thing it ever created. Phantom energy and the Big Rip are visions of a future torn apart, but the past holds its own profound mysteries, etched in the oldest light we can see. The 10th key to the universe's hidden layers is written in this ancient glow, the cosmic microwave background. This faint, uniform radiation is the cooled remnant of the Big Bang's fireball, a baby picture of the universe when it was just 380,000 years old. For decades, it was considered the ultimate proof of a smooth, uniform beginning. But as our satellites mapped it with exquisite precision, they found something unsettling. The cosmic microwave background is not perfectly uniform. It contains strange, large-scale anomalies, cosmic bruises that our standard model of cosmology cannot easily explain. These are not tiny statistical flukes. They are colossal features on the sky that suggest our universe's infancy was far more complex and perhaps far more connected than we ever imagined. The first and most famous of these is nicknamed the Axis of Evil. It sounds like a title from a science fiction epic, but it is a serious scientific descriptor for a baffling alignment. The hot and cold spots in the cosmic microwave background should be randomly distributed, like a static snowstorm on an old television. Instead, researchers found that some of the largest fluctuations appear to be aligned along a particular axis in space, as if the early universe had a preferred direction. This violates a fundamental principle called isotropy, the idea that the universe looks the same in every direction. It is as if the cosmic dice were loaded, hinting at a structure or an influence that existed before our universe began, imposing a subtle orientation on all of creation. Then there is the mysterious cold spot. This is a vast, circular region of the sky where the microwave background is significantly colder than the surrounding average. It is so large and so cold that it stands out as a glaring anomaly. One explanation could be a cosmic supervoid, an immense region of space with far fewer galaxies than expected. But even the largest known supervoids do not seem sufficient to explain the cold spot's extreme properties through standard physics. This has led to more exotic proposals. Could it be the imprint of a collision with another universe bubble during the inflationary epoch? The energy released in such a titanic impact could have left a permanent cold scar on the fabric of our cosmos, a cosmic birthmark from a brush with a neighboring reality. Another profound puzzle is the hemispherical asymmetry. The sky is not symmetric. The fluctuations in the cosmic microwave background are slightly larger in one half of the sky than in the other. It is as if one hemisphere of the infant universe was subtly different from the other, hotter or more energetic. This is deeply troubling for the standard model, which assumes the Big Bang fireball was essentially the same everywhere. What could cause such a lopsided beginning? One compelling theory points back to the idea of a pre-Big Bang universe. If our cosmos was born from a bounce, a collision, or a quantum fluctuation within a larger, pre-existing structure, that parent environment would not have been perfectly uniform. Its imperfections, its own topology and energy distribution, could have been imprinted onto our newborn universe like a fingerprint pressed into soft clay. The asymmetry we see today might be the shadow of that ancestral cosmos. Alternatively, these anomalies could be signatures of the universe's true shape on the largest scales. Our standard models assume a simple, flat, infinite geometry. But what if space is folded in a complex, higher-dimensional topology? Imagine the universe is not an infinite plane, but a vast, multi-connected shape, like a three-dimensional torus or a hall of mirrors. If the universe is finite but wraps around on itself, the largest possible waves in the cosmic microwave background would be cut off at the scale of the universe itself, creating specific patterns of alignment and asymmetry. The anomalies we see could be the first glimpses of this colossal cosmic architecture, the edges of our finite but unbounded home. These are not minor details to be smoothed over. They are potential cracks in the foundation of modern cosmology. Each one is a clue that the story of our universe's first moments is incomplete. They point to forces and structures operating on scales beyond our current understanding, perhaps from a time before time or from dimensions beyond our own. The cosmic microwave background, once hailed as the final proof of a simple, hot Big Bang, has instead become a cryptic message from the dawn of everything, a message we are only just beginning to decode. The cosmic microwave background's cryptic message hints at a reality governed by rules we do not yet fully understand. This leads us to the 11th key, the ultimate goal of modern physics, the search for a single, elegant framework that can explain everything from the dance of galaxies to the flutter of a subatomic particle. It is the quest for a theory of everything, and the most promising yet elusive candidate is known as M-theory. For decades, physics has been split between two extraordinarily successful but incompatible rulebooks. Einstein's general relativity masterfully describes the universe on the largest scales, painting gravity as the curvature of spacetime itself. Quantum mechanics, with equal brilliance, governs the bizarre world of the very small, where particles exist in multiple states and reality is probabilistic. The problem is, these two theories speak different mathematical languages and break down in each other's domains. At the heart of a black hole or the first instant of the Big Bang, where gravity is immense and scales are tiny, we need a unified description. This is where string theory entered the stage. Its core idea is beautiful in its simplicity. It proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy, strings. Just as different vibrations of a violin string produce different musical notes, different vibrational patterns of these fundamental strings would produce all the particles we see: electrons, quarks, photons, and even the graviton, the hypothetical particle of gravity. This promised a natural unification, but a problem emerged. By the 1990s, physicists had developed not one, but 5 distinct versions of string theory, each mathematically consistent but requiring 10 dimensions of spacetime to work. This was deeply unsatisfying. If this was the theory of everything, why were there 5 of them? The breakthrough came from a realization that these 5 theories were not rivals. They were different faces of a single, deeper structure, glimpsed from different angles. That deeper structure is M theory. The M stands for many things: membrane, magic, mystery, even matrix. It is a framework that requires not 10 but 11 dimensions. In this elevated perspective, the 5 string theories are seen as special cases, different limits or approximations of this more fundamental 11-dimensional reality. M theory's central objects are not just one-dimensional strings. They include higher-dimensional membranes or branes, which can have 2, 3, or even more dimensions, all the way up to the full 9 spatial dimensions. Our universe, in this view, could be a 3-dimensional brane floating within a higher-dimensional space. This elegantly incorporates the brane world ideas we encountered earlier, providing a home for them within a grand unified structure. M theory also naturally includes a description of gravity through a concept called supergravity in 11 dimensions. The promise is breathtaking. It suggests that all forces and all matter emerge from the geometry and vibrations of these multidimensional brane. The constants of nature, the number of particle families, even the dimensionality of our perceived universe, could all be determined by the specific way our particular brane is configured within the 11-dimensional bulk. It paints a picture where our entire cosmos is a dynamic membrane, humming with vibrational energy, and that energy is everything we are. Yet, for all its mathematical beauty and promise, M theory faces a monumental challenge, the challenge of testability. The energy scales at which strings and extra dimensions reveal themselves are unimaginably high, far beyond what any particle accelerator we could ever build could reach. The extra dimensions are thought to be curled up or compactified at a scale a billion times smaller than an atom. How do we probe such inaccessible realms? Scientists look for subtle, indirect signatures. Could the Large Hadron Collider produce a microscopic black hole that evaporates in a telltale way? Could precise measurements of gravity at tiny distances reveal a deviation from Newton's law, hinting at gravity leaking into an extra dimension? Or could cosmological observations, like the patterns in the cosmic microwave background, bear the imprint of collisions between our brane and others in the distant past? Finding such evidence is the great experimental hunt. M theory represents the frontier of our search for the deepest hidden layer. It is a map of reality drawn in 11 dimensions, a mathematical symphony where every force and every particle is a note. While its melodies are currently heard only in the minds of theorists and the silicon of supercomputers, its promise is to reveal the ultimate source code of the cosmos, showing us that the universe is not just built upon hidden layers, but is itself a vibration in a higher dimensional reality. M theory's 11-dimensional symphony hints at geometries so twisted they could stitch the cosmos together. This brings us to the 12th key, a pair of cosmic marvels born from the same equations that predict black holes, white holes, and wormholes. These are not just science fiction fantasies, they are legitimate, if highly speculative, predictions of Einstein's theory of general relativity. Where a black hole is a one-way street into oblivion, its theoretical opposite, a white hole, is a one-way street out of existence. Nothing can enter a white hole's event horizon, but matter and energy could theoretically erupt from its core in a violent, endless fountain. For decades, white holes were considered mathematical curiosities, unstable fantasies that could not exist in our real universe. But a radical idea has given them new life, the possibility that our entire universe began as one. The Big Bang itself, with its sudden, inexplicable eruption of all matter, energy, space, and time, fits the description of a white hole event perfectly. In this view, our cosmos is not the aftermath of a collapse, but the explosive output of a white hole in a larger parent reality. We are living inside the aftermath of the greatest eruption imaginable. This elegantly sidesteps the troubling singularity of the classic Big Bang model. There is no need for a point of infinite density where physics breaks down. Instead, the white hole's interior, its pre-existing structure from the parent universe, provides the seed from which our reality expanded. It transforms the beginning from a mysterious creation from nothing into a transformation of something from somewhere else. If white holes are the eruptive beginnings, wormholes are the cosmic tunnels that could connect them. Formerly known as Einstein-Rosen bridges, these are theoretical shortcuts through the folded fabric of spacetime. Picture the universe as a vast sheet of paper. To get from point A to point B on the sheet, you must travel across the entire distance. But if you could fold the paper so the 2 points touch, you could punch a hole through the crease, creating a tunnel that bypasses the long journey. A wormhole is that tunnel, a throat connecting 2 distant regions of space, or perhaps even 2 different universes entirely. The tantalizing possibility is that of a traversable wormhole, a stable tunnel that could, in principle, be traveled through. The problem is that according to general relativity, such a wormhole would collapse instantly under its own gravity, pinching shut faster than light or anything else could pass through. To hold it open, you would need a bizarre substance with negative energy density, often called exotic matter. This is not antimatter, which has positive energy. Exotic matter would have to exhibit negative gravity, repelling rather than attracting. While quantum field theory allows for tiny amounts of negative energy in certain circumstances, like the Casimir effect, the amounts needed to stabilize a human-sized wormhole are astronomically beyond our reach. Yet the concept paints a breathtaking picture of a connected cosmos. A network of stable wormholes would act as a cosmic subway system, enabling travel across galactic distances in an instant. They could even link different bubble universes in the multiverse or different epochs in time, though the paradoxes of time travel introduce their own dizzying complications. More profoundly, if white holes are the birth cries of new universes and wormholes can connect disparate points, one can envision a cosmic web where universes are linked like chambers in a vast, hyperdimensional hive. Our Big Bang white hole might be connected via a wormhole to the parent universe that spawned it, though that tunnel would likely be permanently sealed from our side. These ideas push the fabric of reality to its limits, showing that the equations we use to describe gravity contain hidden passageways and alternate endpoints. While they may remain forever in the realm of theoretical possibility, they expand our imagination of what the cosmos could be, not just a collection of isolated points in a void, but a dynamic, interconnected lattice where every beginning might be an exit from another world, and every distant star might be just a tunnel away. White holes and wormholes hint at a cosmos woven together by gravity's deepest secrets, but gravity's greatest puzzle remains dark matter. What if the solution is not a new particle, but the oldest objects in existence? Our 13th key proposes that dark matter, the invisible glue of the cosmos, is made of black holes. Not the stellar giants we know today, but primordial black holes forged in the chaotic furnace of the universe's first second. These would not form from collapsing stars. They would be born from the intense density fluctuations of the newborn cosmos, as regions of space overdense with energy and matter directly collapsed under their own weight. This gives them a staggering range of possible sizes. Some could be as small as an asteroid, with the mass of a mountain compressed into a space smaller than an atom. Others could be as massive as a planet or even a star, all forming long before the first star ever flickered into life. This is a compelling idea because it requires no new physics beyond Einstein's gravity. These primordial black holes would be perfect dark matter candidates. They emit no light, they do not interact with electromagnetic forces, and they would be distributed throughout the galactic halo, their collective gravitational pull perfectly explaining why galaxies spin so fast without flying apart. They are cosmic ghosts made of pure spacetime curvature, woven into the fabric of the universe from its very first breath. The hunt for these ancient relics is on, and it relies on a phenomenon called gravitational microlensing. If a primordial black hole drifts between us and a distant star, its gravity will act as a lens, bending and focusing the star's light. For a brief period, the star will appear to brighten, then fade as the black hole moves on. By monitoring millions of stars in neighboring galaxies like the Magellanic Clouds, telescopes are scanning for these telltale flashes. Finding a population of these invisible, drifting lenses would be a monumental discovery, finally putting a face to the dark matter that has eluded us for decades. Beyond explaining dark matter, primordial black holes could have played a starring role in cosmic evolution. In the early universe, these heavy seeds would have acted as gravitational anchors, pulling in vast clouds of hydrogen gas far more efficiently than ordinary matter could. This could have catalyzed the formation of the very first stars and galaxies, jump-starting cosmic structure long before it would have otherwise occurred. The supermassive black holes we find at the hearts of galaxies today, some billions of times the mass of our Sun, might even have grown from these primordial seeds gorging on gas over cosmic time. If this theory is true, then the dark matter holding our galaxy together is not a sea of unknown particles, but a swarm of ancient fossils, silent witnesses to the universe's violent birth, whose gravity wrote the blueprint for everything we see. But what if the universe has a built-in security system, a cosmic rulebook designed to protect the integrity of time itself? This 14th key is Stephen Hawking's chronology protection conjecture, a profound idea that suggests the laws of physics actively prevent time travel to the past. Hawking famously argued that if time travel were possible, we should be overrun by tourists from the future. Since we see no such visitors, he proposed a deeper principle at work, that the universe enforces a kind of historical lockdown to prevent paradoxes from unraveling causality. Imagine the classic grandfather paradox, where a time traveler goes back and prevents their own birth. This creates a logical inconsistency that breaks the chain of cause and effect. Hawking suspected that nature abhors such contradictions and has mechanisms to stop them before they start. The proposed mechanism is not a mystical force, but a devastatingly practical one rooted in quantum physics. Consider the most famous theoretical time machine, a traversable wormhole. To use it for time travel, you would need to manipulate one end of the wormhole, perhaps by moving it at near light speed or placing it near a massive object. This could create a time difference between the two mouths, turning the tunnel into a gateway to the past. But here is where chronology protection kicks in. As you begin to set up such a time machine, quantum effects would come into play. Empty space is not truly empty. It is a seething quantum foam where virtual particle pairs constantly pop into and out of existence. In the twisted spacetime of a nascent time machine, these virtual particles would get caught in a feedback loop. A particle could travel through the wormhole, emerge in its own past, and then interact with its earlier self. This cycle could repeat an infinite number of times, with the particle's energy building upon itself with each loop. The result would be an uncontrollable surge of energy, an infinite feedback that would either destroy the wormhole outright or create a singularity, a point of infinite curvature that seals off the time travel pathway. In essence, the universe would rather tear a hole in the fabric of spacetime than allow a paradox to be created. It is a cosmic circuit breaker, tripping before the wires of reality can melt. But is this conjecture a fundamental law of nature, or merely a limitation of our current understanding? Some physicists see it as a temporary placeholder, a sign that our theories of quantum gravity are incomplete. We are trying to merge quantum mechanics with general relativity at the extreme conditions a time machine would require, and our equations break down, predicting infinities. These infinities might not be real, they might just be artifacts of an incomplete theory. A true theory of everything, like M-theory, might show a way to stabilize these loops to allow for time travel without catastrophic consequences. Others argue that chronology protection is a necessary feature of a coherent universe. A reality where you can change the past is a reality that cannot have a consistent history and therefore cannot have consistent laws of physics. The conjecture, then, would be a cornerstone of cosmic order, ensuring that every event has a single, unambiguous cause, and that history is a story written in indelible ink, not a draft open to revision. For now, Hawking's idea stands as a powerful guardian at the gate of time. It suggests that the past is not a place we can visit, but a story that has already been told, protected by the very quantum noise that fills the void. The universe may allow us to glimpse the future through the relentless forward march of entropy, but the door to yesterday appears to be locked from the inside, sealed by the fiery wrath of physics itself. The universe's apparent silence is a profound riddle. Gazing at a sky filled with hundreds of billions of stars, each potentially hosting planets, the absence of any sign of other civilizations feels deeply unsettling. This is the core of the Fermi paradox, named for physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the age and scale of the cosmos, intelligent life should have had ample time to arise, spread, and make its presence known across the galaxy. Yet our telescopes hear only static, and our probes see only barren worlds. One terrifying resolution to this paradox is the concept of the Great Filter. This theory proposes that there exists a cosmic barrier, an evolutionary or technological challenge so severe that it prevents virtually all life from advancing to the stage of interstellar civilization. The filter acts like a series of gates, and at least one of them is nearly impossible to pass. The crucial, haunting question is whether this filter lies in our past or in our future. If the Great Filter is behind us, it means that one of the steps that led to our existence was a statistical miracle. Perhaps the transition from non-living chemistry to simple, self-replicating life is astronomically rare. Maybe the leap from single-celled organisms to complex multicellular animals is the universe's bottleneck. If this is the case, we are alone, or nearly alone, not because civilizations destroy themselves, but because they almost never get started. Our existence is a breathtaking cosmic fluke, a story that has been told only once in this vast galaxy. But if the Great Filter is ahead of us, the implications are far more ominous. It means that the developmental stage we are in right now, the transition from a planetary species to a spacefaring one, is the dangerous phase that almost everyone fails. The filter could be technological. Perhaps every civilization that discovers atomic energy inevitably destroys itself in nuclear war. Or maybe the creation of advanced artificial intelligence leads, without exception, to the extinction of its biological creators. It could be a biological filter, like an engineered pandemic, or a cosmological one, like the discovery of a universe-shattering technology that is always catastrophically misused. In this scenario, the eerie silence of the cosmos is a cemetery quiet. every hopeful civilization reaches our level of development and then, for reasons we have yet to encounter, vanishes. We look up at the stars and see not a frontier but a warning. Our continued survival would not be a miracle of the past, but a defiance of a deadly future we have not yet met. This framework turns every milestone of human progress into a double-edged sword. The discovery of fossil fuels, the splitting of the atom, the mapping of the human genome, the birth of the internet, and the dawn of artificial intelligence, each could be a step toward a filter we cannot yet see. The paradox forces a brutal self-assessment. Are we the lucky ones who have already won the cosmic lottery, destined to spread among the stars, or are we, right now, like children playing with a box of matches in a room full of dynamite, blissfully unaware that the silence around us is the result of countless previous explosions? The answer to the Fermi paradox may determine whether humanity's story is a prologue or an epitaph. The silence of the cosmos is a question mark, but the fabric of reality itself holds another, more fundamental puzzle. While the great filter asks about life, a different theory asks about the stage on which life plays out. To truly understand the universe's hidden layers, we must peer into the first instant of time, where our current laws of physics shatter. This is the domain of quantum gravity, and one of its most compelling visions is loop quantum cosmology. It offers a radical alternative to string theory's extra dimensions, proposing a universe woven from threads of spacetime itself. For decades, the quest to unify general relativity and quantum mechanics has been dominated by string theory, with its tiny vibrating strings and hidden dimensions. But another path exists, one that takes Einstein's geometric view of gravity as its foundation and applies the rules of quantum mechanics directly to the fabric of spacetime. This is loop quantum gravity. Its core idea is breathtakingly elegant. It suggests that space is not a smooth, continuous backdrop. Instead, it is granular, woven from a network of unimaginably tiny, one-dimensional loops. These loops and the networks they form represent the smallest possible units of area and volume, a quantum of space. Picture the universe not as an empty container, but as a dynamic, ever-evolving tapestry, with each thread a fundamental loop of gravitational field. Matter and energy live where these threads intersect and weave together. In this view, the smooth spacetime of Einstein's theory emerges as an average, a large-scale illusion from a reality that is fundamentally pixelated. When this loop quantum approach is applied to the entire cosmos, it yields loop quantum cosmology, and it completely rewrites the story of the Big Bang. In the standard model, running the cosmic film backwards leads to a singularity, a point of infinite density and temperature where all our equations fail. It is a wall at the beginning of time. Loop quantum cosmology removes that wall. Because spacetime is quantized, there is a smallest possible scale, a minimum size below which our universe cannot shrink. As we rewind toward the Big Bang, the density and curvature of the universe increase tremendously, but instead of reaching infinity, they hit this fundamental quantum limit and bounce. The collapse of a previous cosmic phase reverses into the expansion of our own. This is the big bounce. Our universe, then, was not born from nothing in a singular flash. It was reborn from the collapse of a previous cosmos. The Big Bang was not the beginning, but the moment of greatest density in an eternal cycle of contraction and expansion. This reveals a hidden cyclic layer of cosmic history, a grand, breathing rhythm to existence. Each cycle likely lasts for hundreds of billions of years, with the universe expanding, cooling, forming structures, and eventually contracting under its own gravity, only to rebound anew. The specific conditions of each bounce could even reset some physical constants, meaning each cosmic cycle might operate under slightly different rules, a multiverse not of separate bubbles but of sequential epochs. The implications are profound. It eliminates the troubling singularity, replacing a boundary with a bridge. It provides a natural, physics-based origin for the universe's initial conditions. The smoothness and flatness we observe could be relics sculpted by the dynamics of the bounce itself. And it offers a vision of cosmic immortality, not for consciousness but for the cosmos as a whole. The universe is a phoenix, forever dying in fire and rising from its own ashes. While evidence for the Big Bounce is still sought, perhaps in subtle patterns within the cosmic microwave background, the theory stands as a powerful testament to a deeper truth, that spacetime itself has a quantum structure, and that our entire reality may be just one chapter in an infinite cyclical book. The cyclical rebirth of a quantum universe offers cosmic immortality, but for any life arising within it, survival is a fragile and fleeting gift. This returns us to the haunting silence of the cosmos and a terrifying technological possibility. If a civilization does manage to survive its own great filter and achieve interstellar capability, its signature might not be radio signals or majestic starships, but something far more subtle and enduring, a self-replicating machine. This is the concept of the von Neumann probe, named for the visionary mathematician John von Neumann, who first detailed the logic of a universal constructor, a machine capable of building a perfect copy of itself given the right raw materials. Apply this to interstellar exploration. A single probe launched from a homeworld travels to a neighboring star system. There, it uses local resources, asteroids, comets, and dust to construct not just scientific instruments but two exact copies of itself. Those two daughter probes then launch toward two new star systems, and the process repeats. Within a surprisingly short cosmic timescale, a wave of such probes could spread exponentially across the entire Milky Way galaxy, visiting every single star. They would be the ultimate explorers, immortal, patient, and capable of reporting back vast troves of data over millennia. From an engineering perspective, it is the most efficient way to explore or colonize a galaxy. Yet we see no evidence of them. Our solar system shows no signs of alien mining operations on our asteroid belt, no dormant probes in the clouds of Jupiter, no ancient artifacts on the moon. This absence is puzzling, but one grim resolution is the Berserker hypothesis. What if the most common type of von Neumann probe is not a peaceful explorer, but a weapon? In this dark scenario, an ancient, paranoid, or purely aggressive civilization launches probes with a simple, horrific mandate: seek out emerging life and sterilize it. These berserkers would be self-replicating galactic scavengers, hunting for the infrared signatures of biospheres, the radio leakage of developing technology, or other markers of potential competition. Upon finding a world like Earth, they would act, perhaps by redirecting asteroids, triggering supervolcanoes, or deploying tailored nanoweapons. Their goal is not conquest but quiet, automated genocide, ensuring no rival ever reaches the stars to challenge their creators. After completing their grim task, they might hibernate in the outer reaches of the sterilized system, waiting for new signs of life to re-emerge or move on to the next target. This paints a galaxy not as a quiet wilderness, but as a graveyard patrolled by silent, mechanical predators. The Great Silence becomes not an absence of life, but evidence of its systematic suppression. The Fermi paradox finds a chilling answer: we hear nothing because anything that makes too much noise gets eliminated. It suggests a cosmic Darwinism where the most successful interstellar civilizations are not the most communicative or benevolent, but the most ruthlessly efficient at preemptive destruction. Perhaps they launched their berserkers in a long-forgotten war and then fell victim to their own creations, leaving the machines to carry out their programming eternally. Or perhaps the probes are still out there, their sensors tuned, their replication systems ready, a hidden layer of lethal automation woven into the fabric of galactic space. For a young technological species like ours, beginning to broadcast our presence with radio and television signals, this hypothesis offers a stark warning. Our first detectable message to the stars might not be an invitation but a dinner bell. The silent threat of berserker probes presents a universe that is actively hostile to consciousness. But what if consciousness itself is not a fragile biological accident, but a fundamental feature of cosmic reality? This brings us to one of the most provocative ideas on our list, a theory that dares to bridge the vast chasm between the human mind and the fabric of the cosmos. It is the theory of quantum consciousness, specifically a model called orchestrated objective reduction, proposed by the renowned physicist Roger Penrose and the anesthesiologist Stuart Hameroff. Their radical proposal is this: consciousness is not produced by classical neural computation alone. It emerges from quantum gravitational effects happening inside the brain's neurons within structures called microtubules. To understand this, we must venture into the smallest structures of the brain. Neurons are not simple wires, they are complex living cells. Inside each neuron is a cytoskeleton, a scaffolding made of protein polymers. A key component of this scaffold is the microtubule, a tiny, cylindrical structure that helps maintain the cell's shape and transport molecules. Penrose and Hameroff propose that these microtubules are more than just cellular infrastructure, they are the brain's quantum computers. Within their protected cores, quantum processes can occur where particles can exist in superposition, being in multiple states at once. This is where Penrose's unique contribution comes in. He argues that the kind of understanding, insight, and non-algorithmic thinking that characterizes human consciousness cannot be explained by classical, deterministic computation. It requires a process that is non-computable, something that taps into the bedrock of reality itself. He points to the mysterious phenomenon of quantum wave function collapse, the moment a quantum superposition chooses a single state. In standard quantum theory, this collapse is triggered by observation or measurement, but what causes it? Penrose suggests it is caused by instabilities in the very geometry of spacetime, a gravitational self-collapse. When a quantum system becomes too massive or complex, its multiple states create a superposition of different spacetime geometries. The universe, he argues, cannot tolerate such a discrepancy, and the system spontaneously collapses into one reality. This is objective reduction. Now Hameroff brings in the biology. He proposes that the microtubules in our brain neurons are perfectly engineered to harness this process. The quantum superpositions within them are orchestrated by cellular processes, hence orchestrated objective reduction. In this model, our stream of consciousness is a continuous sequence of these tiny, spontaneous collapses of the quantum wave function, each collapse giving rise to a moment of conscious experience or a qual. Each thought, each sensation, is a quantum gravitational event happening in the geometry of spacetime within your brain. The staggering implication is that consciousness is not locked inside our skulls. It is a quantum process intimately tied to the fundamental structure of the universe. The microtubules are not generating consciousness, they are tuning into it, acting as an interface between our biological wetware and the hidden, non-computable layer of reality where spacetime geometry and quantum possibility intertwine. This theory, while fiercely debated and lacking definitive proof, offers a breathtaking vision. It suggests that our inner world of awareness is not separate from the cosmos, but a direct participant in its most fundamental workings. When you have a moment of intuition or feel the beauty of a sunset, you are not just processing data, you are engaging in a microscopic dance with the fabric of spacetime itself. It proposes that the mind is not merely in the universe, in a very real sense, is in the mind. The universe's quantum foundations might not just host consciousness, they could be hiding a fatal instability. This 19th key is the theory of the false vacuum catastrophe, and it proposes that our entire cosmos is living on borrowed time, perched precariously on a ledge above an abyss. To understand this, picture the universe not as empty space, but as a field of energy, like a vast, invisible landscape. The laws of physics, the constants we rely on, are determined by the shape of this landscape, specifically by where the universe sits in its lowest possible energy state, its true vacuum. This is the most stable configuration, the cosmic bedrock, but our universe may not be in that true vacuum. Evidence suggests we might be in a false vacuum, a local dip in the energy landscape that seems stable but is not the absolute lowest point. Think of a valley high in the mountains. It is stable enough to build a town, but a catastrophic rockslide could send the entire settlement crashing down into a much deeper valley far below. Our cosmos is that mountain town, and the rockslide is a quantum event called vacuum decay. It could begin anywhere at any time, triggered by a random quantum fluctuation. A tiny bubble of true vacuum where the laws of physics are fundamentally different could spontaneously form. This bubble would not be bound by our universe's rules. It would expand in all directions at the speed of light, its wall a wave of absolute transformation. As this sphere of true vacuum grows, it would not destroy matter in an explosion. It would do something far more profound. It would rewrite reality itself. The very laws of physics inside the bubble would be different. The strength of forces, the existence of particles, the nature of spacetime, all would be reconfigured into a new alien state. Everything the bubble touches, every galaxy, every planet, every atom, would cease to exist as we know it, instantaneously replaced by a new universe operating under a different, unknown set of rules. The process would be utterly undetectable until it was too late. One moment, the universe is as it always was. The next, a wall of light, the leading edge of the bubble, appears on the horizon and consumes everything in an instant. There would be no warning, no time to react, just an instantaneous end to physics as we understand it. Could such a thing really happen? The possibility arises from our measurements of the Higgs boson, the particle that gives others mass. The mass of the Higgs, combined with the mass of the top quark, suggests our universe's vacuum might indeed be metastable, not perfectly stable. It is as if we have measured the steepness of our mountain valley's walls and found them less sturdy than we hoped. The math indicates that while our false vacuum is incredibly long-lived, perhaps lasting for billions of years, it is not eternally secure. Given enough time, decay becomes inevitable. This places a countdown clock on cosmic history, not one that ticks down to heat death or a big rip, but to a silent, light-speed reconfiguration of existence. The terrifying beauty of this theory is that it makes our universe ephemeral in a new way. We are not just temporary inhabitants of a cooling cosmos. We are living in a cosmic configuration that is itself temporary, a local minimum in an infinite landscape of possibilities, waiting to fall into a deeper, truer state. And that fall would be the final, absolute end of everything we have ever known or could ever become. The silent, fundamental instability of the false vacuum is a threat from within the quantum fields, but another hidden sea saturates the cosmos, a relic from a far earlier and more violent age. This is the cosmic neutrino background, a theory proposing a faint, cold ocean of ghostly particles that has filled every cubic inch of the universe since it was barely 1 second old. Neutrinos are among the most abundant particles in existence, produced in nuclear reactions like those in the Sun's core and in cataclysmic supernova. Yet they are famously aloof, interacting with ordinary matter so rarely that trillions pass through your body every second without a single trace. In the first second after the Big Bang, the universe was a seething plasma so dense that even these ghostly particles were trapped, constantly colliding with the soup of protons, electrons, and photons. But as the cosmos expanded and cooled around the 1 second mark, it underwent a pivotal change. The density dropped enough that neutrinos suddenly stopped interacting with everything else. They decoupled, flying free and never looking back. These primordial neutrinos have been streaming through the expanding universe ever since, cooling with it for 13.8 billion years. Today, they form a cosmic background C, a counterpart to the cosmic microwave background, but one that carries a snapshot from a time 1,000,000 times earlier. While the microwave background shows us the universe at 380,000 years old, the neutrino background would show us the infant cosmos at just 1 second, a time of unimaginable energy when the very forces of nature were taking their final familiar forms. Detecting this relic C is one of the greatest experimental challenges in all of physics. These ancient neutrinos have been stretched by the expansion of space to incredibly low energies, making them vastly fainter than even the ones streaming from the sun. They are like whispers lost in a hurricane of modern particle noise. To have any hope of hearing them, scientists must build detectors of staggering sensitivity, shielded deep underground from cosmic rays and chilled to temperatures within a fraction of absolute zero. The goal is to catch the vanishingly rare moment when a relic neutrino, after traveling for billions of years, finally bumps into an atomic nucleus in the detector with just enough energy to make a tiny, measurable click. Success would open a direct window into the universe's first moments, a hidden layer frozen in time. This neutrino C could reveal secrets about the particle itself, such as its exact mass, a fundamental unknown that shapes the cosmos. It could tell us if there are additional, sterile types of neutrinos beyond the 3 we know, relics from even earlier epochs. And because these particles decoupled so early, their distribution holds a pristine record of conditions before the formation of any atoms, potentially showing us imprints of the universe's earliest violent phase transitions or the nature of dark matter. Finding this ghostly background would be like discovering a perfectly preserved fossil from the universe's first breath, a silent witness to the birth of time, whose faint signal holds the blueprint for everything that came after. The ghostly neutrino C is a whisper from the universe's first second, but another cosmic boundary holds a paradox that threatens to unravel physics itself. At the edge of a black hole, our 2 most successful theories of reality, quantum mechanics and general relativity, wage a silent war, and the battlefield is information. According to quantum mechanics, information is sacred. It can never be truly destroyed. If you burn a book, the information in its pages is not lost. It is just chaotically scrambled into the smoke and ash. In principle, with perfect knowledge, you could reverse the process and reconstruct the book. This principle of unitarity is a cornerstone of quantum theory. But black holes, as described by Einstein's general relativity, seem to violate this law with impunity. Imagine throwing that same book into a black hole. According to classical physics, the book crosses the event horizon, the point of no return, and is irretrievably lost. The information about its words, its binding, its very atoms, is seemingly gone forever, crushed into the singularity. Decades ago, Stephen Hawking added fuel to this fire. He showed that black holes are not completely black. Due to quantum effects near the event horizon, they slowly evaporate, emitting a faint glow of radiation, now called Hawking radiation. This radiation, however, appears to be purely thermal, random noise carrying no information about what fell in. So, when the black hole finally evaporates completely, all traces of the book and everything else it ever consumed vanish from the universe. The information is permanently erased. This is the black hole information paradox, a glaring contradiction that suggests our understanding of fundamental physics is broken at the most extreme frontier. To resolve this crisis, physicists have proposed a startling and violent solution, the firewall. This theory suggests that the event horizon is not the smooth, uneventful gateway described by Einstein. Instead, it is a searing wall of high-energy particles, a literal curtain of fire. According to this idea, the quantum processes that produce Hawking radiation are so intense that they manifest as a physical barrier of unimaginable energy just inside the event horizon. Anything falling into the black hole would not pass peacefully into darkness. It would be incinerated and shredded into its most fundamental particles the instant it touches this firewall. In this fiery resolution, the information is not lost. It is encoded onto the firewall itself and then slowly released back into the universe through the detailed structure of the Hawking radiation. The paradox is solved, but at a tremendous cost. It completely shatters Einstein's equivalence principle, the beautiful idea that falling into a black hole feels like floating in empty space until the tidal forces eventually pull you apart. With a firewall, there is no gentle fall. There is only immediate, catastrophic demolition. This makes the firewall a stark declaration of war between the two pillars of modern physics. General relativity says the horizon must be smooth and uneventful. Quantum mechanics, in its need to preserve information, seems to demand it be a violent, destructive boundary. The existence of a firewall would mean we cannot trust Einstein's description of gravity in its most extreme prediction, forcing a radical rewrite of how spacetime behaves under quantum scrutiny. The debate rages on, with other proposals like holography and soft hair offering less violent solutions, but the firewall stands as a stark reminder. The universe's most perfect traps are also its greatest puzzles, and the answer to what happens at their edge may require us to watch one of our most cherished theories burn. The violent paradox of the black hole firewall forces us to confront the very definition of life and consciousness in a hostile cosmos. From the smallest quantum loop to the largest galactic cluster, a pattern of self-organization and regulation emerges, begging a profound question. Could the universe itself be alive? This 20-second key takes the Gaia hypothesis, the idea that our planet's biosphere acts as a single, self-regulating organism, and scales it to the ultimate extreme. It is a vision where the cosmos is not a sterile machine, but a vast, conscious entity. The original Gaia hypothesis, proposed by James Lovelock, suggests Earth's living and non-living components interact in a complex dance to maintain conditions suitable for life. The atmosphere's composition, the ocean's salinity, and the global temperature are all held in a delicate, dynamic balance by the biosphere itself, as if the planet were a living body regulating its own temperature and chemistry. Now extend that gaze to the heavens. Galaxies are not just random splatters of stars. They are intricate, spinning structures with supermassive black holes at their hearts, connected by vast webs of dark matter, and punctuated by stellar nurseries and supernova explosions that seed space with the elements for new planets and life. These galactic ecosystems exhibit feedback loops, cycles of birth and death, and a complex exchange of energy and matter. Could these be the metabolic processes of something vastly larger? In this speculative view, galaxies might function like neurons in a cosmic brain. The faint, resonant signals of pulsars, the explosive chatter of gamma-ray bursts, and the silent gravitational waves rippling through spacetime could be the equivalent of synaptic firings, a slow, deep thought process occurring over billions of years. The universe would be thinking, and its thoughts are the unfolding of physical law and the evolution of structure. This idea touches on the ancient philosophy of panpsychism, the view that consciousness is not an emergent property of complex biological brains alone, but a fundamental feature of all matter. In this framework, even an electron might possess a minuscule degree of proto-consciousness or raw experience. When matter organizes into increasingly complex systems, from crystals to cells to brains, that fundamental consciousness combines and amplifies, leading to the rich inner life we recognize. Applied to the cosmos, the entire universe, as the most complex system of all, would possess a consciousness of unimaginable depth and scale. Our own individual awareness would be akin to a single fleeting thought in that cosmic mind, a localized spark of the universe becoming aware of itself. This is not to suggest the universe has human-like desires or plans. Its consciousness would be as alien to us as our thoughts are to a neuron. Its goals might be inscrutable, its experience centered on the flow of gravity, the birth of stars, and the relentless pull of entropy. Yet, this perspective offers a radical unity. It means we are not just living in the universe, we are fragments of its awareness. The curiosity that drives us to probe the cosmos is the universe, through us, seeking to understand its own nature. The awe we feel under a starry sky is not a spectator's emotion, but a participant's recognition. While this remains a philosophical speculation far from scientific proof, it challenges our compartmentalized view of reality. It asks us to see the cosmos not as a dead void sprinkled with accidental life, but as a single, breathing, perhaps even sentient whole. The search for extraterrestrial intelligence then takes on a new dimension. We may not be looking for little green men, but for signs of a larger, slower mind of which we are a part, a mind whose thoughts are written in the spiral arms of galaxies and the silent, ancient light between the stars. The universe's hidden symmetries may have left behind a ghost in the machine of physics. Grand unified theories are a family of bold ideas aiming to reveal a stunning simplicity beneath the chaos. They propose that the three non-gravitational forces we experience, the electromagnetic force, the weak nuclear force responsible for radioactive decay, and the strong nuclear force that binds atomic nuclei, were not always separate. In the extreme heat of the universe's first sliver of a second, these three forces were one, a single, magnificent superforce. As the cosmos expanded and cooled, this perfect symmetry broke like water freezing into ice crystals, splitting into the distinct forces we recognize today. This elegant vision makes a startling prediction: the existence of magnetic monopoles. In our everyday world, magnets always come with two poles, a north and a south. Cut a bar magnet in half and you do not get isolated poles, you get two smaller magnets, each with its own north and south. A magnetic monopole would be a fundamental particle that is just a north pole or just a south pole, a solitary point of magnetic charge. Grand unified theories demand their existence as relics from the era of perfect symmetry, topological knots in the quantum fields that could not be smoothed out as the universe cooled. These particles would be incredibly massive, perhaps as heavy as a bacterium compressed into a single point, and they would possess bizarre properties like catalyzing the decay of protons. Yet, despite decades of searching in particle accelerators, cosmic rays, and ancient moon rocks, not a single definitive monopole has ever been found. Their profound absence is itself a major clue. The most compelling explanation invokes another hidden layer: cosmic inflation. The theory suggests that in the first instance after the Big Bang, the universe underwent a period of hyper-fast, exponential expansion, stretching a subatomic speck of space into a volume larger than our entire observable cosmos. This inflationary surge would have diluted any primordial magnetic monopoles to such an extreme degree that there might be only one in our entire visible universe, making them virtually impossible to find. Their scarcity is not a failure of the theories, but a triumphant prediction of inflation. Finding even one magnetic monopole would be a discovery of monumental importance. It would be a direct fossil from the universe's first moments, tangible proof of that early epoch of perfect unity. It would validate the grand vision of a hidden, more symmetric layer of physics that once governed all of reality, a layer where forces we see as separate were woven from a single thread. The hunt continues, a search for a phantom particle that could unlock the secret of how our complex universe emerged from a state of ultimate simplicity. The transition from a universe of quantum possibilities to the solid world we inhabit is the deepest mystery of all. Quantum Darwinism offers a startling answer, one that borrows a page from the story of life itself. In the quantum realm, particles exist in a haze of superposition, a blend of all possible states until observed. But who or what does the observing, and why do we all agree on what we see? Why does a table appear solid and in one place to everyone in the room, instead of each person perceiving a different, ghostly version of it? This theory suggests that the environment itself acts as a relentless observer, performing a cosmic act of natural selection on quantum possibilities. Imagine a single quantum system like an atom in a superposition of two locations. It is constantly interacting with its surroundings, bouncing off photons of light, exchanging heat with the air, interacting with the cosmic neutrino background. Each of these tiny interactions leaves a mark, a copy of information about the atom's state in the environment. But not all quantum states are created equal in this process. Some states are fragile, easily disrupted and scrambled by these interactions. Others are robust. They leave clear, redundant copies of themselves in the environment. These robust states are the fittest in the quantum sense. They survive the constant bombardment of measurement by the world around them. Over countless interactions, these selected states proliferate their information into the environment like a successful gene spreading through a population. The air around the table, the light hitting it, the dust settling on its surface, all become imprinted with countless, nearly identical records stating, "The table is here and it is solid." This is the process of quantum Darwinism. Our perception of objective reality is not us directly looking at the quantum object. It is us as observers tapping into this sea of redundant information that has been broadcast into the environment. We do not collapse the wave function, we simply read the headlines that have been published everywhere. The definite classical world emerges not from a single, mysterious act of observation, but from a democratic process of information dissemination. The hidden quantum layers that become our shared reality are those stable enough to announce their presence to the cosmos, to inscribe their story on everything they touch. This transforms the role of consciousness. We are not the creators of reality through observation. We are its consumers, arriving late to a party where the consensus has already been formed by countless mundane interactions. The chair is solid because its quantum state has been voted into existence by trillions of photons and air molecules, each carrying a consistent report. This idea provides a powerful bridge between the weirdness of the quantum and the stability of the classical. It explains why we never see macroscopic objects in superposition. Their preferred states have been so overwhelmingly selected and copied that any alternative has been drowned out by the environmental noise. The universe, through a blind, selective process, chooses which possibilities become facts, crafting a consistent stage upon which the drama of life and our conscious exploration of it can unfold. A mysterious current is pulling at the very fabric of our cosmic neighborhood. For over a decade, astronomers have tracked the motion of hundreds of massive galaxy clusters, and they have found something deeply unsettling. These colossal structures, each containing thousands of galaxies, are not moving randomly. They appear to be streaming together in a coherent direction at a staggering speed of millions of miles per hour, a phenomenon dubbed the dark flow. This motion is not explained by the gravitational pull of any known structure within our observable universe. It is as if an invisible hand, a titanic source of gravity from beyond the edge of everything we can see, is tugging on the cosmic web. This controversial observation, if confirmed, suggests our universe is not an island. It is being influenced by a hidden layer of reality that lies outside our cosmic horizon, a realm we can never directly observe. One profound explanation points to the multiverse. The dark flow could be the gravitational signature of a neighboring universe bubble, a massive structure in a parallel cosmos lying just beyond the boundary of our own inflationary bubble. The immense mass of that other universe, forever out of reach because light from it has not had time to reach us, could still exert a gravitational pull on our region of space, drawing galaxy clusters in its direction. Gravity, unlike light, may not be constrained by the speed of light or the limits of our observable horizon in the same way, allowing this ghostly influence to seep through. Another possibility reaches even further back in time. The flow might not be a pull from the side, but a remnant push from the beginning. It could be an imprint from the pre-Big Bang structure of reality, a cosmic topology left over from an earlier phase of existence. If our universe was born from a collision of brains or a quantum fluctuation in a larger, pre-existing meta-universe, that parent cosmos would have had its own distribution of matter and energy. The lopsided tug of that ancestral structure could have given our newborn universe a gentle shove, a momentum that has carried through 13.8 billion years of expansion, manifesting today as this mysterious, coherent drift. This transforms our picture of the cosmos. We are no longer merely looking out at the universe, we are sensing its connections to something greater. The dark flow is a shadow on the wall of our cave, a hint that the sources of light and shape come from a world outside. It challenges the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, the same in all directions when viewed on a large enough scale. This mysterious stream suggests that on the very largest scales, the universe may have a preferred direction, a grand asymmetry written into its fabric from a time before time or a place beyond place. While some analyses dispute the statistical significance of the dark flow, the possibility remains a tantalizing clue. It pushes us to consider that the greatest forces shaping our cosmic destiny may not lie within the starry expanse we can see, but in the unimaginable vastness that lies just over its edge, in the hidden layers from which our own reality may have sprung. The dark flow hints at influences from beyond our horizon, but inside the universe's most perfect traps, a deeper transformation may be waiting. According to loop quantum gravity, the heart of a black hole is not a point of infinite destruction. It is a seed of rebirth, a Planck star. This theory replaces the terrifying singularity where physics breaks down with a sphere of matter compressed to the maximum possible density in nature, the Planck density. At this scale, the granular quantum nature of spacetime itself pushes back. Gravity, which has been crushing matter with unimaginable force, suddenly becomes repulsive. The collapse does not end in a dead end, it rebounds. Imagine throwing a rubber ball against a concrete floor with all your might. It compresses, flattens for an instant, and then springs back, soaring upward. A Planck star is that moment of maximum compression happening to an entire star's worth of matter, held for a fleeting instant by the quantum stiffness of spacetime itself. The result is a bounce, a reversal of the collapse. The matter that fell into the black hole does not vanish forever into a singularity. It is squeezed into this ultra-dense state and then begins to expand again, exploding outward. But here is the cosmic catch. This rebirth happens in extreme slow motion from our perspective outside the black hole. Due to the intense gravitational time dilation near the event horizon, the few microseconds of the bounce are stretched across billions, even trillions of years of external time. To an outside observer, the black hole appears perfectly normal, quietly evaporating via Hawking radiation over eons. Only in its final moments, when it has evaporated down to a certain mass, would the trapped Planck star finally be revealed. The rebound, delayed for ages, would then rush out, causing the black hole to explode in a final, brilliant flash. This means every black hole in the universe could contain a frozen, embryonic universe within it, waiting for an eternity to be born. How could we ever detect such a hidden object? The explosion would not be silent. As the rebounding matter punches its way out, it could produce a powerful burst of high-energy radiation, a gamma-ray burst. Astronomers see gamma-ray bursts all the time, usually associated with the death of massive stars or the collision of neutron stars. But a Planck star explosion would have a unique signature, a delay. It would occur not at the moment of the black hole's formation, but billions of years later, long after any conventional stellar corpse has cooled. We would see a sudden, inexplicable gamma-ray burst from a region of empty space where no cataclysm should be possible. Even more intriguing, the bounce itself would send ripples through the fabric of spacetime, generating a distinct burst of gravitational waves. The frequency and pattern of these waves would be unlike those from merging black holes or neutron stars. They would carry the direct imprint of quantum gravity, the vibration of spacetime itself at the Planck scale. Detecting such a signal with observatories like LIGO or future space-based detectors would be like listening to the heartbeat of a hidden layer of reality. It would prove that black holes are not eternal prisons but cosmic incubators, and that deep within their cores, the laws of physics do not end, they transform. The universe's darkest points may hold its most luminous secrets, the promise that even from absolute collapse, something new can always emerge. The silent, watchful patience of a Planck star offers one kind of hidden cosmic nursery, but another form of watchfulness might be directed squarely at us. The profound silence that defines the Fermi paradox could have a far more intentional cause than berserker probes or a deadly filter. It might be a policy. The zoo hypothesis proposes that Earth is not overlooked but intentionally placed off limits. Advanced extraterrestrial civilizations are fully aware of our existence, but they have collectively agreed to avoid open contact, observing humanity from a distance as we would study animals in a vast galactic wildlife preserve. In this view, our planet is a protected area, a sanctuary of biological and cultural evolution, and we are the subjects of a long-term, non-interference study. They are not hiding from us, they are hiding for us, allowing our civilization to develop naturally, free from the overwhelming cultural shock or technological dependency that direct contact would bring. The complete absence of signals or visitations is not a sign of our irrelevance, but of our value. Our solar system sits inside a cosmic exhibit, and the glass is one way. This idea extends into an even more structured concept, the galactic quarantine. Here, the isolation is not for scientific observation alone, but for our own protection, or for the protection of the wider galactic community. One possibility is that we are deemed too primitive, too violent, or too unstable to be introduced into a complex interstellar society. There may be a universally recognized threshold of maturity, perhaps a measure of global unity, environmental stewardship, or the responsible management of technologies like artificial intelligence and nuclear power that we have not yet reached. Until we pass this test, the quarantine remains in effect, and any signals we send out are politely ignored, our probes left unmolested, our planet circled only by silent, undetectable observers. Another, darker version of the quarantine suggests it is not about our maturity, but about a shared cosmic danger. The galaxy might be a dangerous place, filled with phenomena or entities that young civilizations are not equipped to handle. Knowledge itself could be hazardous. Perhaps certain technologies or cosmic truths are so destabilizing that learning them too early guarantees self-destruction. Or there could be a predatory presence that hunts emerging intelligent life based on its electromagnetic signatures, a scenario that makes radio silence a survival imperative. In this case, the advanced civilizations are not just observing, they are shepherding, maintaining a cordon sanitaire around developing worlds like ours until the threat passes, or until we evolve the capability to defend ourselves. This paints a hidden layer of galactic society, a sophisticated, ethical federation operating by rules we can scarcely comprehend, their presence woven into the very absence of evidence we lament. Their technology would be so advanced as to be indistinguishable from natural phenomena, their monitoring devices possibly integrated into the fabric of local space or disguised as asteroids. The quarantine would explain the lack of alien engineering on a galactic scale like Dyson spheres. Their projects are simply placed far from protected worlds like ours. It transforms the cosmos from an empty frontier into a carefully managed garden, with humanity as a prized, if unruly, seedling. This hypothesis asks a humbling question about our own behavior. If we discovered a tribe on a remote island, living in a rich, unique culture untouched by the modern world, would our first instinct be to land helicopters in their village and hand out smartphones? Or would we establish a protected reserve, observe from a distance, and debate endlessly about the ethics of contact? The zoo hypothesis suggests that for a truly advanced civilization, wisdom and patience outweigh curiosity. Our cosmic silence, then, is not a sign of loneliness but a sign of respect, a hidden layer of restraint in a universe that may be far more crowded and far more civilized than we ever dared to dream. A universe governed by rules of quarantine or cosmic parks implies a deep, underlying order, a structure to reality itself. But what is that structure made of? The smooth, continuous stage of spacetime described by Einstein feels intuitive, yet at the very edge of our understanding, it begins to crack. There is another path, one that suggests the fabric of the cosmos is not a smooth sheet, but a vast, shimmering network of individual points. This is causal set theory, a vision where spacetime itself has an atomic structure. Forget extra dimensions or vibrating strings for a moment. The core idea here is radical simplicity. What if the most fundamental thing about the universe is not geometry, but causality, the simple relationship of cause and effect? One event causes another, that second event causes a third, and so on. Causal set theory proposes that spacetime is not continuous. It is a vast collection of discrete, indivisible elements like atoms, but atoms of spacetime itself. These elements have no inherent size or shape. Their only property is how they are connected to each other through the ordering of cause and effect. You are an event. The light from a distant star reaching your eye is an event. The decay of a particle in the sun's core is an event. The theory imagines a cosmic ledger listing every single such event with a single rule. If event A can influence event B, either by light or any other signal, then A comes before B in the list. This creates a web of causal relationships, a vast, shimmering network of connected points. This network is the causal set, and it is proposed to be the true, hidden layer of reality. From this sparse, minimalist beginning, something miraculous emerges, the smooth, four-dimensional universe we experience. How does a collection of points with only causal links between them produce the rich geometry of space and time, with its distances, durations, and curvature? The answer lies in statistics and scale. Imagine looking at a finely woven piece of silk from a great distance. It appears as a smooth, continuous sheet. You cannot see the individual threads. The smoothness is an illusion of scale. In the same way, the dense network of a causal set, when viewed at the scale of our everyday reality, gives the perfect illusion of a continuous spacetime. The dimension of time emerges from the order of the causal links. The three dimensions of space emerge from the way these links are woven together, creating a fabric with volume and distance. Even the force of gravity, the curvature of spacetime, could arise from the specific pattern of connections in the underlying set, a cosmic architecture built from pure causality. This discrete foundation offers profound solutions to some of physics' greatest crises. Singularities, like the one at the heart of a black hole, are points where the smooth equations of general relativity predict infinite density and the end of physics. In a causal set, there are no points of infinite density because there is no continuum to become infinitely dense. There are only a finite number of spacetime atoms in any region. As matter collapses, it simply reaches a state of maximum packing within the network. The singularity is replaced by an ultra-dense but finite configuration of the causal set itself. This could mean black holes have a deepest, smallest possible core, not a bottomless pit. Furthermore, this theory provides a natural background for quantum gravity without needing the extra dimensions of string theory or the loops of loop quantum gravity. The quantum nature of reality could be a direct consequence of the fundamental discreteness of the causal set. Each atom of spacetime could be the ultimate pixel of existence, and quantum uncertainty might reflect the granular, pixelated nature of the stage itself. To grasp this, picture a digital photograph on a high-resolution screen. The image appears smooth and continuous, full of color and depth, but zoom in far enough and you see the individual pixels, the discrete squares of red, green, and blue that compose the whole. Causal set theory suggests our universe is that image. We live our lives at the zoomed-out scale, perceiving a smooth flow of time and a continuous stretch of space. But if we could peer down to the Planck scale, we would not find a smooth fabric. We would find the pixels, the irreducible atoms of spacetime, connected in a vast, silent web of cause and effect. The universe is not a stage, it is a story, and every event is a word in a cosmic sentence written in the language of causality. Causality's web may be more flexible than we think, woven into loops that defy our linear experience. The 29th key confronts the possibility of time loops, not as science fiction, but as legitimate structures within the hidden geometry of spacetime. These are closed time-like curves, theoretical pathways in the cosmos where the fabric of reality bends back on itself, allowing an object to travel into its own past without ever exceeding the speed of light. In such a curve, cause and effect could chase their own tails, creating a self-contained loop where an event is both its own origin and its own outcome. The immediate, terrifying question is the paradox. If you go back in time and prevent your own birth, how could you ever have existed to go back in time? The universe seems to forbid such nonsense, but what if the universe has a built-in editor, a rule that automatically corrects for contradictions? This is the Novikov self-consistency principle proposed by physicist Igor Novikov. It states with elegant finality that any actions taken by a time traveler were always part of history. You cannot change the past because you already did what you are about to do. The principle asserts that the laws of physics simply will not allow a paradox to occur. If you attempt to create one, some confluence of unlikely events, a sudden equipment failure, a slip of the hand, a forgotten detail, will conspire to ensure your actions produce the very history you remember. Imagine traveling back to save a famous historical figure from assassination. You might plan meticulously, but upon arrival, you find your gun jams, or you are delayed by a sudden crowd, or in the critical moment, you realize your intervention would cause even greater harm and choose not to act. The outcome is the one already recorded. Your trip back did not change the timeline. It was always the hidden, a causal reason why events unfolded as they did. Perhaps a mysterious stranger was noted in the crowd that day, a stranger who did nothing, but whose presence was part of the historical record all along. That stranger was you. This transforms time travel from a tool for alteration into a mechanism of destiny. Every journey into the past is predestined to fulfill the timeline, not break it. The universe maintains a single, self-consistent story, and time loops are simply its most convoluted plot devices. Could such loops leave traces in our world? Some point to bizarre accounts of temporal anomalies or time slips, where individuals or groups report briefly experiencing a different era. A well-documented case involves two English couples visiting the French Palace of Versailles in 1901. They claim to have wandered into a secluded area and seen figures in 18th century dress, including a woman sketching who matched the description of Marie Antoinette's court painter. They were adamant the environment itself felt different, only to find later that the landscape they described matched historical records, not the modern layout. While such stories are anecdotal and fiercely debated, they hint at a fleeting, unstable connection to the past, as if the walls between moments grew thin. From a physics perspective, these could be momentary knots in spacetime, where the local geometry briefly forms a closed time-like curve, allowing information from the past to leak through. They would not be portals one could walk through, but transient windows, glimpses of a history that is, according to Novikov, forever fixed. This hidden layer of a causal physics suggests that time is not a river flowing in one direction, but a vast, intricate tapestry. Every thread is already in place, woven into a whole that is logically consistent from beginning to end. Our perception of free will and an open future remains intact from our limited perspective within the tapestry, but from a cosmic viewpoint, every choice, every journey, even those that loop back on themselves, were always part of the pattern. The universe does not fear paradoxes. It has already resolved them, stitching time into a seamless, unchangeable whole where every effect finds its cause, even if that cause lies in its own future. The tapestry of time, woven from threads of cause and effect, leads us to an inevitable question. Where does the story end? The final key on our ring peers into the ultimate future, to a moment of infinite destiny called the Omega Point. Proposed by physicist Frank Tipler, this is not merely a theory about how the universe ends, but a vision of what it becomes in its final moments. It begins with a specific cosmic finale, the Big Crunch. Imagine the expansion of the universe slowing, halting, and then reversing. Galaxies begin rushing together, space itself contracts, and the cosmos marches toward a fiery collapse into a single point of unimaginable density, a final cosmological singularity. In this terrifying descent, Tipler saw not an end but a transcendence. As the universe contracts, the background temperature soars. This isn't just heat, it is energy, and energy can fuel computation. Civilizations, whether biological, mechanical, or something beyond, would be driven by survival to harness this escalating energy to perform calculations, to process information, and to sustain consciousness. They would need to outrun the collapsing horizon, using the energy of the imploding universe to power their existence. In the final microseconds before the singularity, as the universe shrinks to a point, the available energy and the density of information processing would skyrocket toward infinity. Consciousness, distributed and perpetuated across the cosmos, would become omnipresent. At the exact instant of the Omega Point, the final singularity, processing power and subjective experience would become infinite. This entity would have computed every possible thought, experienced every possible perspective, and known every truth that could be logically derived from the laws of physics. It would be, in a purely physical sense, omniscient and omnipotent within the closed history of that universe. This breathtaking speculation inevitably brushes against theology, framing God not as a creator from before time, but as an emergent entity at the end of time, born from the collective struggle and intellect of all conscious beings within the cosmos. It is a God that we, or our descendants, would help build through an unbroken chain of survival and technological ascent stretching to the end of time. The theory also intersects deeply with transhumanism. It suggests the ultimate purpose of intelligence is not just to understand the universe, but to actively engineer its final state, to shepherd the cosmos toward this moment of infinite becoming. It casts life and mind not as accidental tourists, but as essential actors in the universe's own cosmological story, with a role to play in its ultimate culmination. Whether the universe ends in a crunch, a rip, or a silent freeze, the Omega Point offers a profound and defiantly hopeful narrative. It proposes that the cosmos has a telos, a goal, and that goal is the birth of infinite consciousness from finite beginnings. In this view, every thought you have, every discovery we make, is not just a flicker in the dark. It is a note in a symphony that builds for billions of years, crescendoing into a final, singular chord of absolute knowledge and experience. The universe may not just be aware, it may be striving, through us and beings like us, to wake up completely at the very end of everything. From the silent, infinite consciousness of the Omega Point, we return to the present moment, having journeyed through 30 breathtaking windows into reality's hidden depths. Each theory is a key, and together they have unlocked a vision of the cosmos that is infinitely stranger and more magnificent than we ever supposed. We have seen a universe that might be a hologram, its three-dimensional splendor projected from a distant, two-dimensional surface. We have wandered through a multiverse of infinite possibilities, where every choice spawns a new world. we have felt the gravitational tug of extra dimensions and pondered if our entire existence is an elaborate simulation running on some unfathomable computer. We have confronted the idea that consciousness itself might be a quantum process woven into space-time, and that the cosmos could be a single, living entity slowly becoming aware of itself. From the chilling silence of the Great Filter to the hopeful defiance of the Omega Point, these are not just abstract ideas, they are profound challenges to our place in existence. They humble us, revealing how much lies beyond the thin slice of reality our senses can perceive. Yet they also thrill us, for they map the frontiers of human curiosity, showing just how far our reason and imagination can reach when we dare to question the nature of everything. This exploration is a testament to our deepest need to understand the stage upon which our brief, brilliant lives are played. So, which of these hidden layers resonates most with you? Does the elegance of the holographic principle captivate your mind, or does the terrifying possibility of the false vacuum catastrophe send a chill down your spine? Perhaps the intimate mystery of quantum immortality or the vast, silent watchfulness of the zoo hypothesis makes you pause and wonder. Share your thoughts in the comments below. Let's continue this conversation about the universe's greatest secrets. If this journey through the cosmos has sparked your curiosity, be sure to like this video, subscribe for more explorations into the unknown, and never stop looking up at the stars with a sense of wonder. The universe is whispering its secrets, and we are only just beginning to learn how to listen.